All right, morning, everybody. Can you hear me? All right. So no technical difficulties this morning. Able to log in. Hopefully, we're gonna have multiple rooms going on. Though I only see 25 participants. Check the waiting room. Okay, announcement. Lab this week is all about getting our mark installed on your computer. Thank you. So this is challenging. We would do this normally in a lab setting. So, people who had Monday Lab already went through this, but this would be in a Monday Lab. We would come in, you'd bring your own computers. I mean, not Monday Lab, but in a in-person lab. Come in, bring your own computers, and you could either use the lab computers or get our mark installed on your machines. Because UNR is all distance learning now, we have to do it on our own machines no matter what. So it is a lot of troubleshooting. If you're using a Mac, you might need to update to the latest operating system, Catalina, before lab. That'll speed things along. If you had an operating system that was outdated and you were in the Monday lab, feel free to join Wednesday and we can get our mark installed on your computer. It involves using a little bit of command line or terminal commands and a few things. Windows is pretty straightforward actually, but if you're a Mac user, it's a little more difficult. You have to do a few things with permissions and downloading the right packages and Fortran compilers. So it's not straightforward, but the good news is once you have it on your computer, you're good to go pretty much for the rest of the semester. And we'll need that for open population models, among other things. Alrighty. So today we're talking about capture, recapture population models. We started off on this lecture on Monday, but then realized we had about half the class in one lecture and half the class in another lecture, and some other issues. So we just went over the exam. And so now we're on open capture, recapture population model. So big picture overview. A few lectures ago, we started talking about estimating abundance. And estimating abundance is critical for a lot of wildlife management and conservation because it's important to know how many animals are in a population. We talked about many methods so far for estimating abundance. Those were started off with a complete census, which is totally unrealistic for wildlife populations. Then we talked about plot sampling, which is also called design-based sampling, where you can develop designs and make estimates about the population. This is kind of what people do for human surveys and other surveys where things aren't trying to hide. And then an extension of plot sampling is estimating detection probability using distance sampling, where we know animals that aren't close to us are harder to see, or we make that assumption and we can fit models to do that. And then after distance sampling, we talked about a number of models called closed population capture recapture models, and those included M0, MT, MH, and MB. And those are all closed population capture recapture models where the critical assumption is the population is closed. There's no births, deaths, immigration, or emigration. And we can estimate abundance using those methods if we don't have those dynamic processes going on. So that allowed us to estimate both abundance and detection probability as long as we have that strong assumption. But now we're going to relax those assumptions and talk about open population capture recapture models. So we're going to permit the populations to die. We're going to permit recruitment of new individuals into the population, and then emigration and immigration. Let's see, so this is what I just talked about. There are 4 fundamental population processes in dynamic populations: births, deaths, immigration, emigration. And we can say the population size at time t plus 1 equals the population size at time t, plus the number of births into the population, plus immigrants, minus deaths, minus immigrants. So we are interested in estimating these parameters and testing hypotheses about them. For example, we might want to know, we could observe that a population was changing using closed population capture recapture models if we conducted that survey, say, each summer, if we did multiple samples within a summer to get those estimates of detection and abundance, we could determine that the population was changing, if it was going up or down. But now we're interested in more specific details about the population. Why is the population changing? Is it because death rates have increased or death rates have decreased? Or is it because animals are coming in from somewhere else? So we can ask those types of questions when we estimate open populations. All right. So here's a schematic of that. We have a ball and urn example where in our previous models, we had a closed population where we didn't have any holes in this population. It's just the animals that were there were there. And we could estimate how many were there doing that. Now we can incorporate births, immigration. We want to incorporate births and immigration, and then deaths and immigration, these dynamic processes. Here are some of the main open capture recapture models. These aren't all of them. This is an open area of research in wildlife methods. Some of my research focuses on developing methods to estimate these population size or building new extensions to these models. But here are kind of the cornerstones of open capture recapture models. So if you know these ones, you have a very good basis or foundation for estimating wildlife population dynamics. The first one is Cormack-Jolly-Sieber model. And what the Cormack-Jolly-Sieber model or CJS model allows us to do is estimate survival rate based on recapture and resighting of marked animals. So this is the main parameter here that we can estimate is survival probability. The next one is the Jolly-Sieber model. So Jolly-Sieber model is an extension of the Cormack-Jolly-Sieber model. Seems they excluded Cormack in this extension when they're developing it. And the extension here is they're going to make an additional assumption that's going to allow them to estimate recruitment and population sizes. So CJS models allow us to estimate survival rates and detection probability. The Jolly-Sieber model is also going to allow us to estimate recruitments and then total population size. The third one is a known fate model. Known fate models we can use when we know when certain animals die. So if we have radio transmitters on those animals, we'll know when they die because we'll get a signal from the radio transmitter and we can go and determine how that animal died and where that animal died. So known fate models allow us to estimate survival rates when fates of individuals can be determined with certainty. We can also use these for looking at nest success models. Because if we find a nest, we can keep going back to that nest to see what the fate of that was. And then band recovery models are used to estimate survival rates when we put out bands on animals and then those bands are returned from dead animals. These are most widely used in waterfowl for setting waterfowl harvest regulations. So people go out every year and ban lots of ducks and geese. And then after a hunter harvests those ducks or geese, they report those bands to the bird banding laboratory. And then they have a big database of all the bands that have been put out. And then when you get birds that are harvested, you can estimate survival rates. So we're going to talk about CJS models today. So CJS models, the basic premise is we're going to go out and capture some animals. We're going to release those animals, and then we're going to go recite the animals. So this is a lot like closed population models, except we're going to make some assumptions that's going to allow us to estimate survival rates, not just population size. Actually, we're not going to estimate population size with CJS models. We're just going to estimate survival rates. Now, when we develop models, so we are in a model-based framework. So this entire class is basically about using models to estimate what wildlife populations are doing. And when we develop these models, we can look at it in two ways. The first way is our estimates are only applicable to the animals that we're observing. So if we capture a subset of animals and then we release them and then we go and recite those animals, and we estimate survival rates from that using a CJS model, we can say that our survival rates apply to the animals, only the animals that we captured, and they don't necessarily apply to the rest of the population that we didn't capture and mark. So that's where we say here it's a conditional CMR model where parameter estimates are conditional on animals being captured, marked, released, and recited. However, if we make an assumption that the animals we capture are representative of the entire population, then we can extend our estimates of survival rates to the entire population, but it all hinges on that assumption. So other animals in the population that are not marked do not contribute to the parameter estimates. We're only basing our parameter estimates on marked individuals. And whether or not we can make the assumption that our marked individuals represent the entire population depends on a couple things. One, that the marks don't affect the animal survival rates. And two, that the animals were selected relatively randomly from the population. All right, so we're focusing on marked animals to estimate survival and detection probability in CJS models. Those are the two main parameters that we're interested in, phi and p. So that little symbol here is the Greek symbol for phi, and then we have p, which has always been our estimate of detection probability. All right, so Cormac developed his analysis from this video. Let me pull this up and see if it works here. I might have to share my screen. Here are fulmars. Let's get a little wildlife in here just by actually looking at some wildlife instead of some equations. Here, they look kind of like a gull. Let's see, do I have any volume? Yeah, they look, for those non-wildlife majors or other people who casually interact with wildlife, they might call this a seagull. But so these are fulmars, and they're really amazing in that they have one of the longest lifespans of any bird species known. They can live up to 80 years long. So the original CJS model was based on these fulmar population data. So let's look a little bit about that. And what they wanted to do when they developed these methods was figure out how can they estimate the survival rates of these fulmars, because it appeared that they had banded individuals that were lasting years and years. They came back. So they wanted to know how well these things survive. So George Dunnett collected capture reciting data on fulmar breeding colony each year. And here's a little quote from, I pulled from somewhere from 2007. It says, the fulmar is one of the longest lived species of birds, possibly achieving an age of 80 years or more. Scottish ornithologist George Dunnett was photographed in 1951 holding a mature breeding fulmar, which he had just ringed. Ringed is a little bit of trivia here. In the US, we call banding birds, we band them, but in Europe, they call it ringing birds. And there's a conference that is focused on statistical methods for wildlife populations called URIN, because of the ring association there. All right, so the bird was, so let's see, Scottish ornithologist George Dunnett was photographed in 1951 holding a mature breeding fulmar, which he had just ringed. The bird was captured again at the same site 30 years later, and George was again photographed with it. He had matured a bit, but the bird looked as young as ever. George Dunnett died in 1995 at the age of 67. The fulmar, it is said, is still around this summer. This was from 2007. Still breeding and apparently untouched by the passing years. Okay, so here's their range here. They breed in the Arctic Circle, up around Alaska, and then over by Greenland here. And then they have a wide migratory route and migrate all the way down south by Baja, California. All right, so fulmars are a gull-like relative of albatross and shearwaters. Albatross and shearwaters are other long-lived birds that they have these huge, long time series of data for. And they can ask some interesting questions when they have data that long. But the northern fulmar is a bird of the northern oceans. It breeds in a few dozen scattered locations off Alaska and Canada, but is more abundant and widespread elsewhere in the northern hemisphere, especially in the northeast Atlantic. Okay, so here's what we're going to do for our CJS schematic. Birds are going to be captured and they're going to be marked with a band that you can either it's going to be a uniquely identifying mark, so you know which individual is which. And after you capture them, you release them back into the population. And we've kind of gone over what can happen already in terms of open population capture recapture models. But here's where that framework actually makes a little more sense. Instead of a population being in the study area or not in the study area, we're going to have some different interpretations. But let me go through here and describe what can happen. An animal can be released. And then after it's released, it can survive to the next time period, or it can die or permanently emigrate out of the population. It survives with probability phi. So we're always going to use phi for survival probability in this class. So phi relates to the probability of surviving from one time period to the next. And that time period is arbitrary. It can be from 1 week to the next week, or it can be from 1 year to the next year, whatever your study design dictates. If it survives, then it can either be recaptured with probability p, or it can be not captured with probability 1 minus p. So p is the probability of recapturing that individual bird. And what do the data look like when we have these schematics? Well, if we release it, it survives, and we capture it, it gets a 1 for the initial capture and release, and then a 1 when we recapture it. And then there's two ways to get 1 and 0. It can get 1 and 0 if we released it, it survived, but we just didn't see it. Or it can get a 1 and 0 if we released it and then it died, and then we would never see it. We would have no probability of seeing it if it died. All right. So as with closed population models, the response variable, we've always used YIT for our data, YIT, for open population models may be summarized by a capture history matrix such that every animal is represented by a row with an identification number as well as its capture history. And its capture history is 1 if it was captured on occasion T and 0 if it was not captured on occasion T. So here's what a capture history would look like here. For individual animal I, it was released at time 0, so we would have all 1s at time 0. And then at time 1, individual 1 was recaptured and individual 3 was recaptured, but individual 2 was not captured that year. However, in the following year, individual 2 was captured and the other 2 were not captured, so they get zeros. So you can envision an Excel table that just has a bunch of 1s and 0s in it, with each row as an individual animal and each column is a time period in which we search for the animal. Okay, now a couple things to note here. If we saw this animal on occasion 2, we know what happened to it here. We didn't see it, but because we saw it in occasion 2, we know it was alive and we just didn't see it on occasion 1. Because it couldn't have died and then came back to life. Same with here. For individual 3, we saw it on occasion 4 and 3, but because we saw it on occasion 4, we know it was alive this entire time. So the fact that we have a 0 here, that we know it was alive this entire time here, but we only saw it 3 out of 4 times, gives us a way to estimate the detection probability. Just naively, we can say, well, it was alive all 4 times. We know that because to see it on time period 4, we had to see it. It had to be alive during all these other time periods. We just didn't see it here. So naively, that gives us about a 75% detection probability with 3 out of 4, seeing it 3 out of 4 times. So we can take these entire capture histories, and when we get zeros followed by 1s, that gives us enough information to actually estimate the detection probability. Same with this 0 here. What we don't know is what happened in this 0 here when we never saw it again. If we see a 0 followed by lots of zeros and we never see it again, we don't know if the animal died somewhere in there, if it permanently emigrated from the study site, or if we just never saw it by chance. All right. So we can break this down into another schematic, just to view it another way, where we have our first capture occasion here. And then so if we release the birds here, and then we come back and recite them here, for an animal to be cited here, it had to both survive this entire period, and that's marked by phi1, and then we had to see it here, and that's indicated by P2. The second, from the second period to the third period, it survives with probability phi2, and we detect it with detection probability P3. So both phi and P range between 0 and 1. They can be any value between 0 and 1. They're not just zeros and ones, but they can be like 0.7 or 0.4, any value between 0 and 1. So let me read through these. At each capture occasion, individuals in the population of interest are captured and or cited. The identity of tagged individuals, for example, the pit tag number, band number, ear tag, color combination, etc., is recorded. Various measurements such as the weight or the mass, the length, other types of measurements can be recorded. And we can use those as covariates to help us understand survival or detection probability. And then unmarked individuals are marked with a unique number. So when we go out and capture new individuals, we recapture old ones, and we can also capture new ones and put tags on those. So, and then all individuals are released back into the population. Data from these capture occasions are used to estimate both the probability of detecting, or the capture probability, the probability of successfully observing the marked individual I during time period T. And then phi again is the apparent survival probability. The probability the marked individual I from the study population during sampling time T survives until time T plus 1 and remains on the study area. And then does not permanently emigrate. So let me say a bit about apparent survival probability. With CJS models, we describe survival by saying apparent survival probability. And what that is doing is putting a caveat on survival. Because when we use CJS models, we cannot distinguish if an animal died or if it just permanently emigrated from the study area. So phi represents the probability of either of those things. Phi is the probability that it died or that it permanently left the study area. So we call that, and we distinguish that from survival probability by calling it apparent survival probability. All right, and this is probably what I just said. The CJS model does not allow us to distinguish between animals that die and those that permanently emigrate from the population. So when we're estimating survival in the CJS models for our BIDE model, we're estimating these two parameters here. Probability of surviving, and 1 minus probability of surviving is the probability of dying. So we get the deaths and then the emigrants. Phi is the probability an animal survives and remains on the study area. Now, if permanent emigration occurs, now if there is no immigration or emigration, and there's just survival, there's just births and deaths, then phi is going to perfectly estimate the survival probability. The apparent survival is going to equal the survival. However, if permanent emigration occurs, phi is going to underestimate the true survival, because actually a lot of animals that are really surviving are just leaving. And those show up in our model and as our apparent survival. If we call that survival, it's going to be a lower estimate of true survival rate. Now, when we move to known fate models in the next couple lectures, we will track individuals that emigrate from the study area to determine their fate, or we delete them from the sample. And in those cases, we can estimate the true survival probability, not just apparent survival. Okay, so 3 important points. We condition on first capture. Individuals do not contribute information about the population parameter estimates until actually they've been captured. So this goes back to my earlier point stating that all of our estimates on our parameters are conditional on the animals that we actually capture. So if for some reason we capture a subset of the population that is weaker than the rest of the population, they may not be representative of the true population estimate. Consequently, parameter estimates apply only to the marked segment of the population unless we assume that they are representative of the population as a whole, and that assumption is going to depend on how you capture animals. Okay, and the second important point is there are two possibilities for individuals with a 0 at the end of their capture history. So if you're looking at all the 1s and 0s, when you get to a 0 and you don't see that individual any longer in your study, the individual died. That's one possibility, and the probability of dying is 1 minus phi. Or the individual survived and just was not detected. So it survived, phi, and it was not detected, 1 minus phi. So a little bit about probabilities here, and we'll come back to this later too. When we're talking about probabilities, we can say the probability of A and B, or we could say the probability of A or B. When we say the probability of A and B, what we do is multiply those two probabilities together. So if A is the probability that it survived, and B is the probability that it was not detected, and we want A and B, we multiply those two probabilities together. That's why we have phi times 1 minus p. But if we were saying the probability of A or B, then we would add them together. So if we wanted to know the probability that it survived or the probability that it wasn't detected, we would say phi plus 1 minus p instead of phi times 1 minus p. Okay, so to estimate p, we use information related to individual caught both before and after time t because these are the only individuals we can be sure were in the population at time t. And that's what I was talking about earlier when if you observe an animal, you know it was alive the entire time before that. Okay, so how do we actually estimate? So the goal here in using these models is going to be estimate phi and p. So how we're going to do that is write out probability statements for each capture history. So what's the probability of observing a 1, 1? What's the probability of observing a 1, 0? And what's the probability of observing this 1, 0? All right, here's one example. Here is our capture history. We saw it. We didn't see it here, but we knew it was alive because we saw it later. We saw it this time, and then we didn't see it this time. So how would we write out this probability? And I'm going to go through this example here to show how we do this. All right, so let me see. It's released in time period t equals 1. So this is our release time here. So after we release it, this 1, we didn't see it, but we know it was alive. So the only way we could not see it, but it be alive is it had to survive and we had to not see it during that time period right here. So it survived, and that probability is phi. And the probability that we didn't see it is 1 minus p2. All right. So then we saw it in time period 3. So we knew it was alive. So that gives us the probability it survived to time period 3 and the probability we saw it in time period 3. And then we saw it here. So it had to survive to this period and we had to see it. So that probability is phi 3 times p4. And then we didn't see it here. So there could be two possibilities here. It could have either died, in which case we wouldn't see it, or it could have survived and we didn't see it. So I'm going to pull out my whiteboard here. We'll take a second break while I get this ready, and let me know if you have any questions on this before we continue.
What was the difference with adding it, the and or adding it or multiplying it again?
Yeah, I'm gonna go over that. I can go over that right now too.
Thank you.
Okay. So let me go to my whiteboard. Here we go. Okay. All right. So now I'm going to go back. I'm going to share my entire screen here. All right. So what we want to do, the goal here is to try and write out how we would get a probability, what the probability is of seeing an animal in both the in time 1 and time 2. In time 1, we mark it and release it. So what's the probability of seeing an animal in the second time? All right, so let's see, where did my, lost my whiteboard. There it is. Okay, finally. All right, so we had released an animal here, and then it could survive. We could see it, we could not see it, or it could just die. So in this case, this is, we saw it. This is didn't see it, but it survived. And this has died. So these are the 3 possible cases that could happen to an animal. So the capture histories that we're going to observe, the data that we're going to observe for this animal here is a 1 and a 1. If that was the case. If this was the case here, where it survived but we didn't see it, then we would see a 1 and a 0. That's what our data would look like. And our data would also look like a 1 and a 0 if it died. Any questions on that part so far? These are 3 possible things that could happen to an animal after we mark it. And the result, and if each one of these things happened, this is the data we would observe. So the question is, how do we write out, there's a lot of things going on here. Well, there's 2 things going on here. There's a survival process and there's a detection process. We want to write out the probability of each one of these events occurring. All right, so let's look at, let's see. Let's look at the first one. Now, for this to happen, going from here to here, it's surviving and we see it. First, it has to survive, and it survives with probability phi. In addition to it surviving, we have to see it, and we see it with probability p. So whatever phi and p are, that's going to describe about how many times we get data that look like this. So if phi equals 1 and p equals 1, meaning they all survive and we see them perfectly if they survive, all of our data are going to look like this. All right, so let's do the second one. This case here. Now, if it survives, we still have the same probability of survival phi, but now the probability of not seeing it is not p, it's 1 minus p. If the probability of seeing it is p, then the probability of not seeing it is 1 minus p. Okay, now if it died, it dies with probability 1 minus phi. That's how it would get to this case here. The probability of that happening, of it dying, is going to be 1 minus phi. We don't know what phi and p are. We're going to use our data, these things, to estimate what phi and p are. We'll use R mark to do that. So we'll have capture histories that look like this. Now, to get to Leela's question, it was, what's the deal with the and or the or? Okay, let's talk about and. So in probability, we have, let's see, we could do the Venn diagram things. If we have A and B, and you say, what's the probability of A and B? So probability of A and B. So that's this little area here. Well, we get that by saying the probability of A times the probability of B. Is that right? I'll come back to that. The point is, if we say, there's a mnemonic we can use. And this is the useful part. Some of these Venn diagrams are useful sometimes, but I'll come back to that. If we say the probability of surviving, let's see, surviving and us seeing it, the way we can calculate the over probability is the probability of surviving times the probability of seeing it. So here's where I was going with that originally. And so the probability of surviving times, so and equals times the probability of detection. And the probability of detection is P, the probability of surviving is phi, so it's phi times P. And that's where this comes from. Same thing with this case here. the probability of surviving and the probability of us not seeing it. So we have the probability of surviving and the probability of not seeing it. Well, the probability of surviving is phi, and means times, and then the probability of not seeing it is 1 minus p. So this is where we get this here. Okay. Now, the last one is just the probability that it died, and that's just 1 minus phi. So that one's a little more self-explanatory. But if we see a 1 or a 0, there in our data, there are two things that could have happened, right? We could have survived and we didn't see it, or it could have died. So this is where we're going to talk about the or. So if the data look like this, we have 1 and a 0, there are two things that could have happened. It could have survived and we didn't see it, and that probability, okay, survived and didn't see it, so we multiply, or it could have just died. And when we have or, that's when we use addition. So this is the total probability for seeing a 1 and a 0. All right, now let's go back to, I want to see if I can share my whiteboard at the same time I share my PowerPoint. It disappears. Where'd it go? All right, I'll just write this down from the slide. So we have a capture history that looks like 10110. So the idea now here is we have to write out what the probability of observing this capture history is. So I have this capture history here. It was released on this time period right here. So we know it was alive up into here, so we can fill in, we know exactly what happened up until this point right here. We can fill in those probabilities. Okay, from here to here, it survived and we didn't see it. So we're gonna say, let me just be, okay. Phi1, it survived that first time period, and we didn't see it in the second time period. And then it survived the second time period. From here to here is the second time period. And we did see it in the third time period. So phi always has a lag on the subscript of 1 compared to p. Not always, but conventionally, that's conventional notation. You can define it however you want, but this is how it's typically done. All right, and then we know it also survived from here to here. So that is phi 3, and then we saw it in that time period, phi 4. Now this last one is the tricky one, from here to here, because two things could have happened. It could have survived and we didn't see it, or it could have died. All right, so let's work out that case. We're going to multiply it by the two cases. So it could have survived the 4th time period, and then we didn't see it in the 5th time period, or it could have died. Okay. Now we can simplify this by multiplying this through and then adding and subtracting, so we get phi 4, phi 4 minus phi 4 p5 plus 1 minus phi 4. These two cancel because we have a positive 1 and a negative 1. And then we have, let's see. Yeah. And then we have all of this stuff still. Times what's left here, which is 1 minus phi 4 p5. And that's what we see when we look at the PowerPoint. Okay, now there's another example, a couple more examples here. 2 more examples. Work these out on your own to make sure you understand what's going on. And if you don't get the right answers that are shown here, let me know and we can work them out together. So we have example 2 and example 3. There's actually several of them here. And then what we can do is we use our data to estimate what P's are and what the P's are. And actually, our mark is going to do all of this for us. It's going to give us the maximum likelihoods for P's and P's for all of them. But this is how it's separating these probabilities out and how we can use these data. Okay. Now, we've got a couple more minutes. Let me go over this one time, actually writing out the model statement for a CJS model. And here's the basic CJS model. We have our data, YIT. This is a matrix of 1s and 0s for capture histories, I, for time period T. This is familiar, this part here. This is the same thing we did with closed population models. So closed population mark recapture models, exact same thing, except different interpretation of ZI. Now I think you'll find ZI makes a little more sense. YIT are whether we observed it or not. That's the matrix of data we have. If the animal was truly alive, ZI equals 1 means it was truly alive, then we're going to see that animal with detection probability P. But if the animal was truly dead, if ZI equals 0, then we'll never see that animal. We won't be able to see it. We're only going to be able to see it if it's alive. Now ZIT follows a Bernoulli distribution again, but with survival probability phi, if the animal was alive in the last time period. If ZIT minus 1 equaled 1, then it's going to survive to this time period with survival probability phi. So the two unknowns in this are P and phi, but we're also going to have some unknowns in the Z's when we don't see the animal. So again, ZI represents this partially known state. We know it when we see the animal. If we see it, we know it's alive. And in that case, we know the Z's. If we don't see it, it could either be alive, where ZI equals 1, just YIT equals 0, or ZIT could be 0 and it would be dead, in which case YIT would be dead. So we have this mixture model here. Now it has to be alive in the last time period to be alive in this time period. Otherwise this equals 0 with probability 1. So if it died last time, or if it was dead last time, it stays dead. But if it was alive last time, it survives to this time period with probability phi. Okay. And then there's some notes on here for your reference. All right. Any questions? And I have office hours too. So for those who have lab today, be sure to update, if you have a Mac, update to the latest operating system if you're okay with that. If you're not okay with that, we'll have to figure out something else.
Just out of curiosity, that program isn't offered on the remote desktop for UNR, is it?
I don't know. So tell me a little bit more about this remote desktop.
I don't know. It's something I have to use for my other classes. It's like a Microsoft thing, and you connect to a desktop. I mean, I don't know how it works, but a desktop, a Windows desktop through the UNR, and so like I've used it for like ArcGIS stuff and NV. But I was just curious; it might be there.
It might be. So you would have to search for program Mark, and if it's there, then you could do it. Mark was installed in all the Cabner computers, so for those that didn't have computers last year, they could use the Cabner computers, and it was already there.
Yeah, I'll try and put it on my computer, but I'll also check because I have to use remote desktop for 2 other classes this semester.
Okay, yeah, that'd be great. Let me know
if it's there.
Yeah, great. Thank you.
I think we did have one of the students last year use the remote desktop and could access it. So.
Oh, really? Okay.
Yeah.
Have a good day.
Thanks, you too.
Actually, if you're staying on for a few minutes, I can like pop over and try and connect and just see if it's there.
Yeah, I'll be here a while.
Oh, wait. I forgot I have a class.
Okay. Let me know when you find out.
Will do.
So regarding lab, you said that it's going to be both this week and next week?
What the main goal for this week's lab is to get everybody's RMark working. Yeah.
Okay. So we don't really have much to do then with our partners if we were able to just get it downloaded?
If you can run RMark and run the commands that are on lab 7 that are posted, then you'll be good. Although I will post lab partners today.
Okay, thank you.
Yeah.